Hello students, this is another question based on work power energy chapter, motion in vertical circle. You can call it a problem based on motion in vertical circle. This is again a very conceptual problem and all of you must pay attention to this. This is what the question says. This is a hemispherical bowl. There is a hemisphere placed on a horizontal surface. There is a block on the top of the hemisphere. A small block having some mass m has been placed on the top of the hemisphere. There is no friction between the hemisphere and the block. There is no friction between the hemisphere and the block, right? Initially the system is at rest. Now we start moving this hemisphere with some horizontal acceleration a. A is constant. You start to push this hemisphere so that it begins to move at a constant horizontal acceleration a. Now the question says, what is the maximum value of acceleration, what is a max, so that the block does not lose contact by the time it rotates through an angle of 1 degree with respect to the hemisphere. Once you begin to push this hemisphere, you give it an acceleration. In the reference frame of the hemisphere, the block will begin moving like this. The question is asking, what could be maximum acceleration for which the block does not lose contact with the hemisphere by the time it rotates through a small angle of 1 degree. By the time the block rotates through a small angle of 1 degree, it should not lose contact with the hemisphere. For this to happen, what should be the maximum acceleration a? If you give it a very huge acceleration, then it may happen that this block will very soon fly off the hemisphere. But the question requires that what should be a max so that the block does not lose contact with the hemisphere by the time it rotates through an angle of 1 degree with respect to the hemisphere. So now you can pause the video and give it a try. You can pause the video and give it a try. Students, actually it is easier to work in the reference frame of the hemisphere to solve this question, because the question itself says that the block should not lose contact with the hemisphere by the time it rotates through an angle of 1 degree with respect to the hemisphere. With respect to the hemisphere. So we will assume that our observer is somebody who is accelerated along with the hemisphere. Observer is somebody who is moving along with the hemisphere. So we are looking at the motion of the block in the reference frame of this hemisphere itself, right? And whatever I am going to say and write will be valid for this observer only. So initially the block is here and after some time it moves to this position. Just to keep the diagram clean and clear, I have shown this angle theta to be large. The question is asking us to discuss a situation where theta is as small as 1 degree, but okay, to make the visuals clear, I have taken a larger angle theta. So let us assume that in some time the block slides from this position to this position. It rotates through an angle of theta with respect to the hemisphere, right? Now, what are the forces acting on this block? Precisely, there are 3 forces acting on the block. One, of course, is the normal reaction, which is along the radius. The other one is weight force, which is vertical, and there is another force, inertial force, pseudo force, what you call it, because our observer is somebody in the accelerated frame. So before he can actually apply Newton's law, he has to add a fictitious force to whichever object he is considering. So this observer is trying to understand the movement of this block. So, in order to apply Newton's law, he has to add a pseudo force, a fictitious force, an imaginary force to the block apart from these real forces. These are real forces, means I can actually tell who is applying normal reaction. It is the hemispherical surface. I can actually tell who is applying this mg force. It is the gravity of the earth. Earth is applying this force. But if you ask me who is applying this force, I do not have a very clear answer. I just know that, means this observer just knows that there is definitely a force m into a in left direction acting on that block, but who is applying that force, he is not sure about that thing. The agency is not certain. The agent who is applying this force is not known. That is why we call it fictitious, imaginary or pseudo force. I am so sorry, but the force is very much there, right? Excuse me for a moment. But the force is very much there, though we do not know who is applying that force. It is a fictitious force. Okay. Now, three forces are acting on this particular block. Now, this block has moved from this position to this position, and let us assume that right now the speed of this block is v. The speed of this block is v. We know that speed of this block was 0 when it was here. So, its speed has increased from 0 to v as it has moved from this position to this position. We can use law of conservation of mechanical energy to relate speed between two positions when a body is undergoing motion in vertical circle. Whenever an object is moving in vertical circle, you can always use law of conservation of mechanical energy to relate speed between any two points. Here speed is 0. We can write speed at this point by applying law of conservation of mechanical energy. Law of conservation of mechanical energy. How do I use this law? The total energy, total mechanical energy at this point is equal to total mechanical energy at this point, right? This is permissible. This is what you do when all the forces which are performing work, listen to me carefully, when all the forces which are performing work are conservative in nature, and moreover you know how to write potential energy for them. For example, if Ma is not there, forget about Ma. Normal reaction does not perform work, so that does not bother you. Then you are left with Mg. Mg only performs work, and you know how to write potential energy for this force Mg, right? When work performing forces are forces like gravitational force, spring force, electrostatic force, you know how to write potential energy for them. In such cases, the law that you use is law of conservation of mechanical energy. But here in this particular question, apart from Mg, there is another force which is performing work. It is Ma, and we have not memorized any potential energy function for such a force. We do not know how to write potential energy for such a force. So, it will be difficult to use law of conservation of mechanical energy here. So, what we use is work energy theorem. Law of conservation of mechanical energy is something that is derived from work energy theorem only. So, what we are going to use is work energy theorem. Again, listen to me carefully. When to apply law of conservation of mechanical energy? When you find that all forces which are performing work, for all such forces which are performing work, you know how to write potential energy, like spring force is working. So, you can write potential energy for that. Mg is working, you can write potential energy for that. So, if only such forces are performing work, you should apply law of conservation of mechanical energy. That is easier. In that case also, if you apply work energy theorem, that is fine, but using law of conservation of mechanical energy is much easier. Now, if you find some force which is performing work, but potential energy for that force is not known to you, then you should use work energy theorem. So, in this case, because Ma is a force for which I do not know how to write potential energy, I haven't studied about it, though I can write potential energy for that also. But we students have not studied about it. So, we will use work energy theorem. What is work energy theorem? Work energy theorem says work done by all forces is equal to change in kinetic energy. Fine. So, work done by pseudo force Ma, work done by gravitational force mg, this will be equal to final kinetic energy minus initial kinetic energy. The initial kinetic energy of the block is 0 and the final kinetic energy is half mv square. So, work done by Ma and work done by mg is equal to final minus initial kinetic energy. Normal reaction does not perform any work. Normal reaction does not perform any work. In this reference frame, this person finds that this block is moving along this arc only. In this reference frame, this man does not see this hemisphere to be moving. So, in this reference frame, this man sees that this block is moving along the curved track, isn't it? Therefore, normal reaction force will not perform any work on this block in this reference frame. So, in this reference frame, the forces which perform work are Ma and Mg. I am so sorry, Ma and Mg. So, work done by Ma plus Mg is equal to change in kinetic energy. Now, what is work done by Ma? Ma is a constant force, isn't it? Because the acceleration is constant, so that pseudo force is a constant force. It is always horizontal, acting in that direction. So, work done by constant forces do not depend on path taken. They are independent of actual path. The work done by such forces can simply be written as dot product of force and displacement. So, in rather simple language, Ma is the force which is horizontal and was acting in this direction. To get its work done, what you need to do is you multiply Ma with this displacement, horizontal displacement. Work done by constant force is simply force multiplied by displacement in the direction of the force. So, Ma is a constant force, work done by Ma is Ma into displacement in the direction of Ma. So, what is this displacement? If this length is r and this is theta, this is r sin theta. So, work done by Ma will be, remember, Ma into r sin theta. It is positive because force Ma is acting in that direction and this horizontal displacement has happened in that direction only. So, work done by Ma force, pseudo force, is Ma into r sin theta. I hope you all understand this. And similar is the case for Mg. Mg is a vertical force. So, to write its work done, we will write Mg into displacement in the direction of Mg. So, how much displacement has happened in the direction of Mg? In vertical direction. This is the displacement in the vertical direction. This is the displacement in the vertical direction. So, as you all can see, this is r cos theta. In this triangle, this is r cos theta, and this is r. So, r minus r cos theta is this length. So, work done by Mg is Mg into r minus r cos theta. So, I have written work done by pseudo force, I have written work done by Mg, and that is equal to change in kinetic energy, which is of course half mv square. Students, in the reference frame of this hemisphere, pseudo force is a force. It is a force. You have to take it as force. So, work done by pseudo force has also must also be included while you are writing work energy theorem. Work energy theorem says work done by all forces, which means all external forces, all internal forces, work done by all pseudo forces, work done by all forces, means every kind of force has to be taken into account. So, work done by pseudo force, work done by gravitational force. Mg force is not performing any work in this case. So, work done by all forces is equal to change in kinetic energy. This is what we have written here. Let me simplify this a little bit. I am writing it like this, mv square by r. I am dividing this by r. So, this becomes ma sin theta plus mg1 minus cos theta is mv square by 2r. Now, it is given in the question that theta is very small. The theta about which we are talking is going to be very small. So, for small theta, sin theta can be written as theta. So, let me write it as ma theta. And in fact, for small theta, cos theta is pretty close to 1. So, if I take cos theta as 1, I need not write this, and this looks reasonable. When this angle is very small, this height is very small, isn't it? So, work done by gravitational force is almost negligible. We can neglect it. So, 1 minus cos theta is almost 0. Let us agree to neglect that. So, ma theta is mv square by r. Let me bring 2 on this side. So, this is the equation that I was looking for. mv square by r is 2 ma theta. Mota moti, this is correct. Now, let us write the equation of centripetal force. Look into the situation carefully. We are observing the motion of this block in this reference frame. In this reference frame, the hemisphere is not moving. The block is simply sliding on this circular path. It is still in contact with the hemisphere. It is sliding on the circular path. So, if the speed of the block here is v, then for radial forces, I can write, you can see here yourself, mg has a component towards center, which is mg cos theta. Normal reaction is away from the center, it is in radial direction, and then ma also has a component this way. This ma will have a component this way. This angle is theta, this is 90 minus theta, this is also 90 minus theta. So, ma cos 90 minus theta, which is ma sin theta. Students, be very careful. mg has a component in this direction, mg cos theta. Normal reaction is in opposite direction, so I will subtract. Component of ma is also in opposite direction, I have subtracted that. So, net force acting on the block towards the center is this much, and this should be equal to mv square by r. We are assuming that block is still on the hemisphere, block is still moving on circular path, it has not left contact with the circular path. So, this is the equation that we get. Now, if I rearrange this to get the value of n, then what do I get? I get mg cos theta minus ma sin theta minus mv square by r, right. This is the value of normal reaction. And in place of mv square by r, I can substitute 2 ma theta. So, I am doing that substitution. Again, take a note that mg cos theta can be written as mg, no harm in that, because cos theta can be written as 1. ma sin theta, again I am writing as ma into theta. For small angle, sin theta is theta, and mv square by r can be written as 2 ma theta. So, 2 ma theta, right. So, this means that normal reaction force is equal to mg minus 3 ma theta, and what do we want? We want that the block should not lose contact by the time angle theta is 1 degree. So, by the time theta is 1 degree, normal reaction should not become 0. So, normal reaction should not become 0 means normal reaction should remain greater than 0. So, if I put normal reaction greater than 0, that means if I make this quantity greater than 0, then what do I get? I get mg is greater than 3 ma theta. mg is greater than 3 ma theta, which means g by 3 theta is greater than a, or in simple language, a should be less than g by 3 theta. So students, acceleration of the hemisphere should be less than g by 3 theta for the block to not lose contact by the time it rotates through an angle of theta, where theta is very small. The normal reaction is greater than 0 till the block has rotated by an angle theta, means the block is in contact with the hemisphere. So now the question says that block should not lose contact by the time theta is 1 degree. So normal reaction should be greater than 0 till theta is 1 degree, which means acceleration should be less than this. So in place of theta we should write 1 degree. Should I write 1? No. This theta should be written in radian, isn't it? I have taken sine theta to be theta. That is valid only when theta is in radian. So don't write theta as 1 degree. Please write it in radian. Pi by 180 radian. Yes. So acceleration is less than 60 g by pi. Please check for any correction, etc. If I think I have done it correctly. So acceleration of that hemisphere should be less than 60 g by